Okay, do you hear me? Okay, it looks like so. So my name is Łukasz Gajowy. I work at Polida at a daily basis, and I'd like to say a few words about Apache Beam. I contribute some to the project, so I think I can do that. And after the talk, I can give you stickers for the project if you want to. If you will be interested, I hope you will be after this presentation. So that's the agenda for this presentation. We're going to talk about some data processing problems that you can face on a daily basis, especially while working with streaming data. Then I'm going to tell you some about Apache Beam and more specifically about its awesome model that is provided, that is implemented in the Apache Beam project. And at the end of this presentation, and we'll have some demos in between, I'm going to tell you about Beam's portability. Portability is currently the most important effort in the community, the biggest one. Lots of developers working on that. So I hope that I will be able to show you what's it about and yeah. So those are this is the link for Slido, and you know probably the drill from the last day, so I won't be talking about that. So let's start the presentation. And let's measure air quality. Back in winter, when I was initially preparing that presentation, I was looking for a good example of a data processing problem that we could actually solve here to see how Beam models handles all that. And I figured that could be a good example, because back in winter everybody was looking at those applications that show you different levels of air quality. And on the backend side, it probably looks somewhat like this. You have a fleet of sensors. Those sensors are scattered all around the various locations and various cities. And those sensors are sending data to a thing called data processing engine, or data processing backend. So that data processing backend could calculate something useful for you. For example, let's say, and let's use that example in the whole presentation. For example, that data processing engine could calculate average dust levels per hour. This dust that you aren't supposed to breathe or you will die eventually. And yeah, so then those applications can show you nice depictions of the air quality. So you've probably all used that. Let's do this. So this is our stream of data. This is how I would depict the situation that is going on in the data processing engine at its edge. You have a stream of data. It's an unbounded stream. And there's lots of events from those different sensors that are sent to that data processing engine. So some of the events, let's say those are the red ones, are coming from Warsaw. They're showing the air quality level in Warsaw. Some of the events are from Gdańsk. Some of them are from Kraków, and so on and so on. And as they approach to our data processing engine, and more specifically, as they are digested by that engine, there appears a notion of processing time. So that's the first important term in our presentation, processing time, which is the time when the events were actually seen by the system, when you could actually do something sensible with them. Before that moment, the events came to the system, to the data processing engine, you had no way of doing anything with the data that the event carry. So now we have the notion of processing time. Now we have some events. If we're hasty, we can think of a solution for our problem, which is calculating average dust levels per each city. So if we're hasty, we can think of a solution like this. We can probably take events from 7 to 8, calculate different levels for air quality per each city, and do that for other time frames and return the results consequently for our users. But is that the correct approach? I'm looking at your faces and I see that you think the same that I am. Obviously, it's not the correct approach. You shouldn't do it like this. Remember, you have a distributed system. If that world was perfect, if there were no delays in the network, if there were no bottlenecks in the network, if your sensors wouldn't become offline, using processing time would probably be an okay idea, right? Because that time probably didn't differ much. That would be okay. But in real life, you have delays over the network, so the measurement happens way before the events actually reach the server. Then your sensors become offline. Even the processing takes time. So those are real problems that you have to solve, and you actually can't solve them that way. Let's look again. Those are the same events that I shown you before, but right now I've wrote some event time at some of them. Event time is the time, obviously, when the events actually happened. So some of the events, like the one at the 8 o'clock, could not be delayed probably at all, maybe a little bit, but that's not noticeable. Some of them could be delayed for 10 minutes. For our problem, this is not a big problem because we are still taking a 1 hour time frame, and they came in that 1 hour time frame. So that's not a problem. They will still be included in the final result. But we have problems with that one that came right after 9 o'clock. That event is delayed for more than an hour, well, more than 45 minutes, but it's after 9. It came to the system after 9. So basically, the situation that will happen will look like this. We will include that event in an improper time frame, and hence our results will be incorrect. So okay, so now we know that we shouldn't use processing time for that stuff, and now we know that for sure. So let's use event time. This seems like the way to go. So right now what we're gonna do is that we're going to take each event, look inside it, and look for something that shows us the event time. It could be some timestamp or whatnot, some notion of event time. And we will look at each event and take that event time and take all events that have event time in a particular time frame and put them in a special place in memory and call it a window, by the way. So we're going to do something like this. We're going to take them, as I said, and stack them somewhere in the memory and wait until we have all the events. But there is another problem. When will we know that we have all the events? But probably never, right? Because how can we know how big is the delay for a particular event? Will it be 3 hours? Because we know that network is usually delayed for 3 hours, or okay, for 15 minutes to be more real, or even less, but there's still delay. Or will it be for days because our sensors are offline and they will come back to the network, connect back to the network after days and release some amount of data? And look at our user experience in our application right now. What is happening? We are not returning anything to the user because we are only taking all the events and stacking it into the memory of the data processing engine, but we are not returning anything because we are still waiting. So maybe, why wait? Maybe we should do something like this. Maybe we should, every hour, return some data based on some incomplete set of data that we've seen so far. So at the upper picture, you can see that I took 3 events that came to me in the first hour. So I'm returning the result based on that. Then take another set of events and update the result based on that. And do that consequently after some period of time. In this case, it's an hour. But even then, we don't really know when to finish this. We don't really know when to finish doing those iterations, those consequent updates. This is actually a totally valid idea to do that because in our case, we have nothing left to do but do that, because we don't know what the delays will be, but we don't know when to stop doing that. So that's another problem here. And in general, this is all one big trade-off. This is one big trade-off that you need to balance. Do you want to have complete data? If you do, you should probably sacrifice some low latency. So this is like a typical banking scenario when you have something to calculate based on a complete data set. Let's say some big money, some banking transactions. And if you want to return a correct result, you have to include all the data. If you want to include all the data, you have to wait for some time. So there will be no low latency in this case. In our case, we should do the contrary, because our user experience will be hurt instead. So we don't want to wait for the complete data set to appear, because if we do, we'll return the result after, let's say, 5 hours, after a week. This is also possible. So we shouldn't do that. We should lie a little bit to our users, but not so much, because that will be an approximation of our result. We're calculating a mean value, so we can probably skip some events, but return something to the users so that they are happy, so that they are actually using our application. Here and there is cost of holding that stuff in memory. So if you are collecting all those events, as I mentioned, where I was talking about windowing, I will talk about windowing in a while later, but while I was stacking that in my memory, this actually required a whole lot of memory. Depending on your case, it can be megabytes, gigabytes, terabytes, I don't know. But this is cost for you, especially in the cloud. And if you're doing many computations, if you're doing many processing units, this is also cost. And you simply have to balance all that in many cases, and it all depends on your case. So here's where Apache Beam comes, and especially its model, its programming model that is useful for solving those problems. It's basically a set of concepts that lets you deal with that stuff, with modeling data processing problems of any kind. It was first described in a paper called the Dataflow paper. It came out in 2015. Then in 2016, Apache Beam was actually open sourced as Apache Beam project. And the term Beam model started to be used, so I'm going to call that model the Beam model. But it's the same as the Dataflow model. This model is unified for both batch and streaming scenarios, and that means that you deal with your data processing problems, whether batch or streaming, in the same way. You do not have separate APIs, separate implementations of a subset of this model for batch and streaming. You have the same model, and you can use all those concepts to work with batch and streaming data. Another nice thing about that model is that it separates all the logic of your algorithm, of your program, from all the technicalities that are underneath. So you don't worry about whether to run on Apache Spark, you don't worry about whether to run on Apache Flink first and then design your algorithm. This is totally decoupled. You think about your problem, and if you solve that problem, you can then decide what should you actually use for, what is actually the right tool for the job, probably because of some performance reasons and stuff like this. And this is especially nice. This is the thing that I like the most in the model. Any data processing problem that you are trying to solve, can be described by answering 4 simple questions. Those 4 simple questions are around different aspects of the algorithm, of the problem that you're solving. And this was actually very thoroughly described in the streaming systems book that I'm going to show you at the end of this presentation. But first, let's answer those questions, and let's calculate average air quality per each city for Poland. So the first question, that I'm going to answer is what do we actually want to calculate. And this is fairly simple. I'm not going to stop for a long time here. It's all about the things that you did in different data processing projects that had some programming models. So it's grouping, so it's filtering the data, it's joining streams of data, it's all kinds of mapping, reducing, and stuff like this. So there's nothing new, but that's the first question, that's the first aspect of your program that you want to focus on. So in Beam, you answer to this using two concepts. The p-transform, which is a transformation that is applied on a collection of data, which is a p-collection. The p-collection is created while you read your data from an input with a special transform called an IO transform. Once you do that, you have a p-collection, and you apply some sort of p-transform, whether grouping, as I said, or doing parallel do operation, which is simply mapping some records to some other records, and so on and so on. And while you do that, while you apply this series of p-transforms, you mix and match your data to achieve the desired result. And then you save that to the output similarly as you've read, but then using another IO transform maybe for some other source. And in code, in our case, this will look like this. We will obviously read some events from in our case, this will be some IO transform that I will show you later. But then we will probably read the values and map them to a key value dataset, so that we have a p-collection of keys and values, keys being cities and values being the dust levels. And after that, we're going to apply a composite transform, which will basically group our data by keys and reduce that using a calculation. In this case, it will be mean value. And that's it. And now watch out. This is something that you're going to see for some times in this presentation. This is a plot between processing time and event time. But you didn't reason about processing time and event time at all at this moment. And this is something that I'm going to highlight a lot in consequent steps, in consequent questions. You only focused on the calculation, right? So what you did is that as processing time advanced, you collected all those events and you just put them somewhere and told your system that you're going to calculate the mean value for that eventually. But I'm not even telling you when. And that's all. This is all we focused right now on. So now it's time, probably, and one important thing, we didn't reason about event time either, right? So let's do that. Let's reason about event time right now, and let's actually let our system gather all those events in that special places in memory I mentioned. So let's do windowing, basically. And windowing is the answer for where in event time are results calculated. Here you think only about event time, and you remember that picture, I just described it, I just reminded you that. And this is basically windowing. So that's the answer, and this is the way of telling your system to look for events with particular event time and group them together to eventually calculate something based on that groups, based on that time frames. So it's different from the previous case where we had this, because right now it's something like this. So you have it grouped, and eventually you'll be calculating the result for each of those windows. But you're not telling when yet. And in code, it looks something like this. You only add one line. We used fixed windows for that. You have different kinds of windows, you can use them, but fixed window is basically the simplest one that is easy to show, so I'm doing that right now. I don't want to show you sessions, but you can actually put your data, you can actually aggregate your data based on user sessions activity based on event time. There are also processing time windows, but I'm not going to talk about them there. Again, look at the streaming book if you're interested in that. So you basically, in the model, have a notion that lets you reason about event time, and this is windowing. So now's the time to answer the question, the ultimate question, when to stop aggregating all those events and when to actually release the result. This is what the third question is for. And we answer to that question using two concepts again. But this time, this will be triggering and windowing. And what is triggering? Triggering is the way of telling your system to actually materialize the data that you've gathered. So you've kept all that data per each window in the memory, and now, based on some signals from the system, you can tell the system to actually release the result, either periodically, or either once, or multiple times based on the amount of data. In our case, the signal that we are going to use to actually return the result is processing time, because we perfectly know that time, so we can say, for example, let's trigger every half an hour, and let's return something based on that time frame in the processing time sense. And with that, we're going to be able to return speculative results, incomplete results every half an hour. But that doesn't solve the problem of actually finishing the windows, closing the windows, right? Because we don't really know when there will be 9 a.m. in the event time sense. So if we don't know that, we are not able to close that window, and we have a problem, because this is somewhat inefficient. This is costly simply to do it like this, because will I iterate 20 times? Will I iterate 40 times to collect our data? What if after 20 times, when I was intending to iterate 40 times, I had all the data, and the next 20 times I actually materialize the results is done for nothing, because I actually have all the events and the results doesn't change. So this is inefficient. So this is why there's windowing. There's watermarks. And watermarks is the system's way of telling you, hey buddy, listen up. You have processing time, you have 8:30 in the processing time sense. And by that point in time, you had all the events up to 8 a.m. in the event time sense. So you can think of that as a function, I would rather say it's a mapping, because there's not only processing time that is an input to watermark. You also look at all the events that you've just collected, and sometimes you have the perfect knowledge about the data source, so you know what events to expect. But this is a kind of oftentimes it's simply a heuristic that is calculated to tell you with a certain probability that you have events up to a certain point in event time. So thanks to that, you can do operations like this. You can simply close the windows, right? So in the first window between 8 and 9, you can see that I have an on-time trigger. This is called on-time trigger. This is a trigger that happens based on a watermark, and the watermark tells you that the window just ended. So you can treat that this is the end of the window, and this is it. But there are also different strategies that you can do with connecting those concepts. So you basically can specify a strategy to trigger early, and this will happen before the window finishes based on watermark. And because, as I said, it's sometimes practical to use a watermark, which is some kind of a heuristic, because you sometimes don't want to wait for infinity for super late events. Then sometimes there is also late data, but the point is that if you ended your window, you can define a strategy to actually handle late events too. And in code, this is done like this. You trigger after the end of the window. This is the on-time trigger. And you have early and late firings, different strategies for different cases. So, okay, right now, we've just talked about assigning to groups based on event time, which is windowing, right? We talked about the algorithm itself. We talked about the data materialization based on two concepts, watermark and triggering. What didn't we talk about? Because I told you that there will be 4 questions. Well, basically, we didn't specify how should the consequent data materializations should relate with each other. What should we do with the data that we're gathering after consequent triggers that are happening per window? And to answer that question, you have, again, different strategies in that model, and you can, for example, accumulate all the events that you've seen so far for a concrete window, for a specific window. So you can say, for example, that after the first trigger, don't toss away all the events that you collected. We will use them after we will have another trigger. So, as you see, the on-time trigger included all the events that have been seen for that window so far. And the other trigger that happened late included even more events. So this is accumulating, and that's one answer, one way to answer that question. And the second way that I'm going to show you, again, look at the book for more, there's also discarding. And this is the cheaper kind of operation, but not applicable to some cases, as you can imagine. Here we toss away all that stuff that was just triggered. So if we trigger, we get rid of all the data that was collected for the window, and we kind of start looking for the data again and collect from the very beginning. So the next trigger will be based on the data that was collected after the first trigger. And so the second on-time trigger will use only one event in this case, and the third, the late trigger, will use only the 2 events, because those were those that were observed after the second trigger. So this is discarding. So in code, you simply attach the strategy for that, and this lets you to actually define different strategies for accumulation, or whether discarding. There's also accumulation and retraction, but it's not implemented in Beam yet, so I'm not talking about that. So basically, we have the model, and it has 4 questions that let you focus on different aspects of your program. And while you answer those questions, it all is easy, relatively easy, to figure out what should be done with event time, with data materialization, and with consequent refinements of the data. So this is how the model is useful, and it was implemented as a core of Apache Beam. We have that model, and thanks to that, Beam is unified for both and batch and streaming scenarios, as I said before. Then Beam aims to be portable and extensible, and those are the next things that I hope you will see on the next slides. The idea is that you have multiple SDKs, Java, Python, Go, that have an APIs that let you use that model, that programming model in code, and there's also a whole set of runners, which is basically some data processing engines, some connections, some way of translating the code to data processing engines, to various data processing engines, and so that you could run that unified model on, for example, Google Cloud Dataflow if you want to run in cloud. And if you didn't, you can always choose to use Apache Flink. And so on, because Beam aims to be extensible. So it means that it should be relatively easy to add new SDKs and new runners. And I'm actually going to show you that in a short demo. That's the code of what we did so far. And we are basically, I basically created some sort of a simulation of air quality sensors, and I'm publishing lots of events to a PubSub topic. PubSub is kind of a distributed messaging system in Google Cloud. It's an equivalent of Apache Kafka, if you're familiar. So basically, I'm publishing them to the PubSub topic. Then I'm subscribed with my pipeline to that PubSub topic, and I'm parsing some content, assigning keys as cities as keys, and dust levels as values. And then I'm applying windows, fixed windows of 10 seconds in this case, because I didn't want you to wait for an hour for a result, right? Or yeah, so basically I also added that speculative approach with early filings. Besides that, we will be firing at the end of the 10-second window. I added a speculative one result that will be returned after 5 seconds. And obviously we're going to accumulate all data here, because we don't want to discard it, because we want to calculate the air quality, the mean value based on all events that we've collected for a particular time frame. So that's the code. That's my, I didn't say one important thing. I'm going to run that first on Apache Flink, and that's the sole purpose of the demo. To run that on Apache Flink, and then run the same code on Google Cloud's Dataflow service. So that's the Flink cluster, and here I'm specifying that I'm going to use the Flink runner. This is like an input argument, input parameter that I have to pass to Beam. And it starts the job. It would be funny if that wouldn't work on a demo that is a video, right? But it won't happen. There's the job. And it actually may not look like you expected. This is because all the optimizations that happened, that middle part was actually squished for performance reasons. We're gonna observe some logs from Apache Flink on the lower console window, and here I'm generating the events. So right now my sensors keep producing the data, and in a while you will see some mean values calculated on the console below. Yep, it starts generating something. The retention of the events to the logs is not so good, because I had very few I was very low on memory, and the calculation also takes time, so yeah. So consequent mean values. The levels in the events are between 0 and 100, and there's a lot of them. So yeah, so it's time to cancel the job, because we're not going to look at Flink forever. It's time to look at Google Cloud Dataflow service. If you don't know that service, it's basically something like Apache Flink. A way to think of that. It's not exactly like this, but it's something like Apache Flink, but in the cloud. And it's a totally different service. It implements the Beam model itself. So now I'm choosing the Dataflow runner, which will connect me to Google Cloud Dataflow service, submit the Beam code, the very same code that I used on Apache Flink. And I actually speeded that up a little bit because of the fact that it has to warm up the cluster for me, prepare workers, because it's an on-demand service. So it has that. It takes about 2 minutes. Yes, it just created. It was 8 times faster, but it created a worker for me, so I can start generating my events. And here you go. In a while, you're going to see that some of the events actually reached our pipeline, and I can calculate mean value based on that. Great, I got some events, so I can show you the logs right now, and there actually are some events collected. So cool. The video demo always works. So as for the current project status, currently there are multiple SDKs and multiple runners, as I mentioned before. Namely, there is the most supported Java SDK, Python SDK, Go, SQL, streaming SQL, where you can use SQL to actually write those pipelines. And there's also Scala SDK. This is basically a Java wrapper, so yeah, so it basically has the same support as Java SDK, a little bit delayed because it's a separate project. In fact, it's not in the Beam's repository. It was developed by Spotify developers, and it's called Shio. As for the runners, you have the most supported Dataflow and Apache Flink. There's also Apache Spark, Apex, Samza, GearPump, and Hadoop MapReduce. There is also ongoing work on Hazelcast JetRunner. You see Hazelcast on the in GeeCON, so I figured that it could be good mentioning that, but it's not officially ready yet. And one important thing, always check out the capability matrices, because all those data processing backends are not supporting everything equally. So yeah, so basically you have to check whether your runner actually can do something for those things that you want to do. So you probably couldn't expect from Hadoop MapReduce to understand Windows. Not Windows, watermarks. And this is kind of connected with portability, because one of the reasons that not everything is supported equally right now is that it was implemented like this right now. So every SDK implements the runner part. So those are totally separate implementations, and because of that you have multiple SDKs also. This is a Cartesian product between SDKs and runners. So every time you want to add a new runner, you have to implement it in multiple SDKs. And it doesn't look very optimistic right now, to be completely honest with you, because only the Java SDK has a whole variety of runners, and Python and Go doesn't have many of them. Also, some differences can emerge between implementations, because this is, again, code duplication between languages. But this is how it looks like now, but in the future, something called Portability Framework will be implemented. This is actually, as I said at the beginning, the biggest effort in the community. This is the way of providing truly portable pipelines in Apache Beam. And in a nutshell, it's going to work like this. You're going to have a set of builders on the SDK side. Every SDK will have its own builder code that will build a unified representation of the pipeline in some unified format. In this case, those will be protocol buffers. So if you don't know protocol buffers, you can think of it as a fancy XML. So you will have that unified representation of that pipeline, and on the runner side, you will be able to interpret that representation along with all the metadata that is there, and actually translate that to a different runner. So adding new SDKs will be as simple as adding that builder part, and all the runners will be supported. And adding new runners will be as simple as adding that interpreting part, and all the SDKs will be supported for that runner. So that Cartesian problem is no more here. And in more detail, it looks like this. There will be a portable runner. There actually is, because it is actually this part is actually finished. So that will translate the code to let's say to the unified representation, to protocol buffers. After that, we will connect to something called job server, and here all staging the artifacts, which is all the jars, all the resources that are required on the data processing backend while invoking the job, and this will happen in the artifact staging service. And there is also a job service that gets the unified representation of the pipelines, optimizes that, so that's the fusion that you've seen in the previous demo, and control all the job invocations, so starting the job, pausing the job, all the states from the that the job can have, collecting all the metrics and everything that is needed. Then the job service will also invoke some runner code part, which will simply translate that optimized representation of the pipeline from protocol buffers to runner's native implementation. So this will let you, for example, run Python code on Apache Flink. But wait a minute, what about libraries that I can't really translate to Apache Flink? What if I'm using TensorFlow in my pipeline for some machine learning? So basically, that's what the SDK harness is for. And this is a Docker container that you will put next to your data processing backend to connect to that with remote procedure calls and run those steps that couldn't be easily translated to runners, to the backend's native code. And once you process that step, you will get back to the pipeline and then proceed with the calculation. So I'm going to show you that now, but this time on a batch scenario. This will be simply counting words, not a very fancy demo, but the fanciness is there. I'm going to run Python SDK on Apache Flink runner. So that's the Flink runner. And that's the batch of text that I'm going to read. It's not so long, so it will be very quick. And now I'm starting the job server for the Flink runner. It will be able to translate all that stuff. And obviously, I will connect not to the from the Python command. I will connect not to the Flink runner, not to the Flink data processing backend, but using a portable runner that will connect to the job service, to the job server, sorry. Because there's also artifact staging. Now the job server got the job, and then it sends it to Apache Flink. And here you can see that it's a whole lot more complicated. This demo was recorded a while ago, about 4 months ago, and that was the state of the project at that time. Now it's better, the job is more, it's better displayed. But here you can see that some of the steps were actually run in the Docker container, because we defined some custom transforms, so they couldn't be translated easily, so they went to Docker. And that's just the proof that it works. The words are counted, so yay. Video demos work. So summing up, we had the 4 questions on the Beam model. It's a nice model, and it's really easy to work with it. It's really relatively easy to get a grasp how to process both streaming and batch data. You have Apache Beam and all its features, and the most importantly, you have portability and its future. Let's hope that it will be great in the future. About the resources, we have the Streaming Systems book. It's a great book. I've read it. I totally recommend it. And it's actually written by Tyler Akidos, Slava Czerniak, and Rowan Lax. And Tyler previously wrote 2 great articles if you're not into reading books, Streaming 101 and 102. So this is like the foundation for the book. And there's obviously Dataflow paper and Apache Beam site. Apache Beam site has lots of documentation. Actually, there's even a section with design documents for portability if you want to dig deeper. And I included yesterday the portability support table because I figured that you would be interested what is the status of portability. Thank you for listening to this presentation. And now it's time for questions. And I think they should appear here, but they don't. I need help. Oh, here they are. Okay. Have you ever used other event processing engine example? Well, the thing is, Beam is not a data processing engine. Beam's the upper layer of abstraction. So you have only the model, and you choose a different data processing engine. So Spark, Flink, Dataflow, what we did on the demo. And I think Esper could be also ported to Beam as the same way as Spark and Flink. I didn't use that, but if that's event processing engine, that maybe it could be ported like this. Isn't the harness Docker a bottleneck? Yeah, well, obviously it is, but it was measured by some engineers, and according to that, it gives an overhead of from 5 to 15%. So it still isn't a deal breaker for some cases where you actually want to use all the other benefits of Beam. Are there any other questions? So thank you. I was really glad to speak about Beam here. And if you're interested, I have some stickers of Beam. Some Beam folks sent me them. So if you want them, I can give you them. Thanks.